The previous section was more or less a kind of preparation for what's coming now, and this is now the central part about determinants, namely determinants of matrices and then of endomorphisms. So first of all, for matrices, let's start right away with the definition. The idea is very simple. We want determinants of n by n matrices, and before we had just n different vectors in k to the n and inserted them into a map to get the determinant, and then it's a quite obvious idea of what we're going to do. We're going to take the matrix and take their row vectors and take them as inputs of the determinants. So the determinant of a matrix is the determinant of the row vectors inserted in the right order. So let n and n, A be an n by n matrix. And please keep this in mind, that sometimes people make a mess with this. We only have quadratic matrices, otherwise determinants make no sense. And this is good enough for endomorphisms because endomorphisms, if we go to they are maps between the same vector space, so especially domain, codomain of the same dimension, which means that any matrix representation of an endomorphism is a quadratic matrix. So as you can probably guess, if we want to go to endomorphisms, we go via matrix representations, and so this is enough for that purpose. Okay, so we have a matrix A, and we let the row vectors be AR1, similar as before, A to ARn, be its rows. The determinant of A is then that A is, the det of AR1 to ARn, and I'm a bit messy, of course, because a row vector, again, I identify a row with a point in k to the n. So just instead of a row, I consider this as a tuple in k to the n. Then this expression is defined as in the previous section. Yeah, this is the definition of the determinant. And just notation, I know that in previous years, some lecturers who did this course had a different notation, which is also quite common and which is totally fine for you to use, namely the absolute value of A. So this is then defined as the determinant of A. I personally don't like this notation too much because it's kind of some confusing in some contexts, but you're totally fine if you use it, so don't worry, that's okay. So just to remember you, so the way that, need more space here, the way the determinant is defined, so with the explicit formula, since the notation I previously used, I labeled the components of the vectors in the previous section in the nice way, so we had this explicit formula, and it turns out that if we take the row vectors, this coincides with the notation we used for matrix entries, or with a way of labeling them, namely the determinant of a matrix which is given by A11 to A1n, A21 to A2n, and so on, to AN1, ANn. Okay, the determinant of this matrix is then the sum over all sigma in Sn, and that was the explicit formula here, the sign of the permutation sigma times A1 sigma of 1, A2 sigma of 2, An sigma of n. This is the explicit formula. And maybe here, if you look at it as a matrix, it might be a bit more intuitive. So if you take a look at these summands, we have, for each number I here in front, we have precisely one factor in this product which has this I in front. So we have one A1 something, A2 something, and so on to An something. This means now we have one element in each row. Now, if we take a look at the sigma of 1, sigma of 2, and so on, this is a permutation. It's particularly bijective. So this means every number between 1 and n appears once here. This means intuitively that in this product, there's precisely one element from every column. So what we do is we take the big sum here with some funny signs, and then here take all products of elements, which we can choose in our matrix, such that we have precisely one element in each row and one in each column. It's a bit like the Sudoku principle. Like if you have a Sudoku, which is completely filled in, if you take if you kind of label all threes, for example, in your Sudoku, you will have one element in each row and one element in each column. So this is basically the Sudoku principle here for determinants, so to say. So one element in each row and each column, and all possible ways of doing so, and then summing this with including some signs here. This is what this does. Now, as a remark, I want to note some special cases, because there are some cases in which we have this formula which looks quite daunting, so to say, in which this becomes more computable. So more explicit computations. Okay, the first case is very simple, 2 by 2 matrices. So what happens there? We have a 2 by 2 matrix, which is of the form A11, A12, A21, A22. So a 2 by 2 matrix with entries in K. Okay, so we need to take the sum of all permutations as n. In this case, this means S2. But, okay, how many? S2 is the set of all permutations of the set 1, 2. But there are not that many. So, of course, we have the identity. And what else can we do? We can just switch the order. We can map 2 to 1 and 1 to 2. This would be the other permutation, but nothing more. So we only have the identity and this map tau, where tau of 1 is 2 and tau of 2 is 1. That's everything. Now, this is a transposition, of course. There's only this transposition of these two. And there we see this is one transposition, so the sign of this is -1. So the sign of tau is -1. The sign of the identity, because nothing happens, is +1. So if we just include this in the formula, this has just two sums, and take a look at what can we do. So the first, so that A11, A12, A21, A22. So what happens here? First we take sigma to be the identity. Then we have A11. So the sign was positive, A11. And A22. Now, this is the first summand, and the second one is coming from the permutation tau. This has this minus sign. So there it's just the other case that here sigma of 1, so here sigma would be equal to tau in this setting, so this would be 2, this would be 1. So we just would get A12, A21, and that's it. So this is the general formula for determinants of 2 by 2 matrices. This is easy to memorize. Since just if you take a look at this, is just taking a cross. We take these two elements, the product here, so here, and then subtract the product of these two elements. So just doing like this. Now, for 3 by 3 matrices, there's also a formula which I will not prove explicitly, but just give you the idea. So now we take an arbitrary 3 by 3 matrix. This means we have A11, A12, A13, A21, A22, A23, A31, A32, A33. So 3 by 3. Okay, what happens here? One checks, first of all. If we take this group as 3, so the set of all permutations of 3 elements, then one needs to think a bit, but it's not that hard to write a list of them. So I just invite you to take a pause at this point and try to write down all permutations. And it turns out there are precisely 6 of them. Precisely 6 elements. So this means the big sum there has 6 summands, 1 for each permutation, the identity being 1. And okay, there are not that many possibilities, and what we then need to do is to figure out the signs. But it turns out because permuting 3 elements is not that easy to, it's not that hard to write them as compositions of transpositions. So this is something where you can really do the math explicitly, which I will not do in detail because it's a bit tedious. A computation of signs shows that the determinant has also a form which looks maybe a bit not that interesting or not that intuitive on first sight, but I will show you how this is. There's a very easy way to memorize this. A3, 1, A3, 2, A3, 3. Okay, first we get A1, 1, A1, sorry, A2, 2, A3, 3. Maybe I can always, at the same time, I can already write down how to memorize this, maybe here below. So, namely, I write two copies of this matrix next to each other. Let's forget about the parentheses for a moment. So this is just here, just scribbling the intuition. Okay, and what we now do is to write a second copy of this matrix precisely next to the other one. Two, 1, A2, 2, A2, 3, A3, 1, A3, 2, whoops, A3, 3. So the first term is this, more colored chalk. Okay, the first thing we're doing is we take the product of these three. So this one here, this gets a plus sign. Now the next one we're taking is the product of A1, 2, A2, 3, and A3, 1. And as we're, so 1, 2, A2, 1, A, was it? No, sorry, 2, 3, A3, 1. And let me already mention the third one, and we will see why this is interesting. So there's a plus A1, 3, A2, 1, A3, 3, 2. Sorry, they're confused. Okay, these are the first three summons. And if you take a look at this diagram in here, these are first this multiplication, if you consider the second copy here there, and then this. So these three appear with a plus. Now there are some more left, and it turns out the remaining ones are, so minus A1, 1, A2, 3, A3, 2, minus A1, 2, A2, 1, A3, 3, no, wait. Yes, it fits. Yeah, sorry. Okay. Minus this, okay, and minus A1, 3, A2, 2, A3, 1. Okay, if you take a look at this, these two, there's also a way to memorize this. So these three guys with the negative signs are those where we have some index the same thing here, 1, 1, 3, 3, 2, 2. So these are the possibilities that come up here. But of course, this formula, I can also never memorize this. But the idea is now here with the plus, we get these three diagonal multiplications. And for the minus signs, there's a similar trick, namely we get, if we take these two matrices again, this is, the first one is 1, 1, 2, 3, 3, 2. This is precisely this diagonal line. This gets a minus. The next one is A1, 2, A2, 1, A3, 3, which is this diagonal line here. And you can guess what's coming now. This is the third one. So plus, 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 minus, minus, minus. And this is the way how to memorize this. Okay, this formula is called the rule of Zarus. And although I didn't prove it in detail, you can, of course, use it from now on. There's a third case, which is, so to say, computable. This time a bit more general, namely the case of upper triangular matrices. So let N in N and A be a quadratic matrix. A with components, with entries A, I, J, as usual. This is supposed to be upper triangular. Just to recall, this means that Aij is 0 whenever I is bigger than j. So if the matrix, scribble this here in the middle, so if we have some matrix So how many rows so on? The only entries which are non-vanishing, this is quadratic, are here in this triangle. So everything below, this is the diagonal here, which we have in a quadratic matrix. Everything below this is just here, we have just 0, 0, 0, and so on. Okay, this is upper triangular. Now, why is this interesting? So if sigma in Sn and sigma is not the identity. Okay, so we have a permutation which really changes something. Then it's easy to see, and this is something that you can really think about this, then there always exists some I between 1 and n with with sigma of I smaller than I. So there will be some element which becomes something bigger than it was, but then there must also be something which becomes smaller than it was. This is something where you can basically write this down and think about a bit, and this is easy to see. I will not give a formal proof of this, which I could do, but God no. So there always exists something like this, but this means, because of this upper triangular case, that then AI sigma of I, the corresponding entry of the matrix, would be 0. But this means, where's my determinant? Up there. So whenever sigma is not the identity, one of these guys is 0. So this means all of the summands vanish except for the one belonging to the identity. So this means the determinant of A is then given as, just the sign of the identity times A11, A22, and so on to ANN, and this is of course plus 1, as I mentioned before. So the determinant of an upper triangular matrix is just the product of the entries on the diagonal. So this is something really useful. This is what we will make good use of. So in this case, I mean, before I said the determinants in general are hard to compute, but if it's upper triangular, I mean, this is what everyone can do. Just multiply everything that's on the diagonal. That's easy. So this is a case where you can really immediately compute the determinant without difficulties, and we will see that we can trace some matrices back to these, so we can compute a lot of determinants of matrices by kind of reforming them into upper triangular matrices and then doing this computation. So this we will see later. But this is a very useful result. So in this case, the determinant is easy to see. Okay, so much for that. Let me quickly erase. We've just seen that determinants of upper triangular matrices are easy to compute. Now, an upper triangular matrix in general, if you study quadratic matrix, we have seen that we can always bring a quadratic matrix into row echelon form by elementary row operations. And it turns out, or just by construction, I think we've already seen this, that the row echelon form of a matrix is always upper triangular. We've seen that this was already a theorem, that all entries on the diagonal are non-zero if and only if the matrix is invertible. This we will make use of later. But there will always be nothing below the diagonal if we're in row echelon form. So if given an arbitrary matrix, quadratic matrix, we can always determine or compute the determinant of its row echelon form. But of course, for this we need to apply elementary row operations to the matrix, and we haven't seen yet what elementary row operations do to the determinants. How do they change them? Can we see this? And this is what we're going to do in the next theorem. So let's take a look at the 3 elementary row operations that we have and take a look at what they do to the determinant. So that n in n and that A be an n by n matrix. Okay, first of all, we had this dropping of rows, and if you take a look at the determinant, its properties, you can almost immediately see what happens. That I and j be numbers between 1 and n, and so that I is smaller than or equal to j. Then the determinant of Sij of A, so swapping 2 rows inside A. If I had an audience, I would now ask who can already see, because it's really easy to see. This is just minus the determinant of A. So B, second type, that was multiplication of a row by some scalar, so that I be an element of 1 to n, and what have we called this, lambda in k without 0. Okay, what happens to the determinant if I multiply, and there I had the notation m lambda I of a, so multiplying the ith row by lambda. And again, looking at the determinant, the way it is defined, this is again something which is really easy to see. This is just lambda times the determinant of a. Now we come to something which is to the third type, which is probably the most complicated thing one could imagine, or this adding of a multiple of a row to another row. So one might now expect that this is kind of the most complicated change in determinant. But let I and j be between 1 and n, and lambda in k, then the determinant of e lambda I j of a. So we add lambda times the jth row to the ith row of the matrix. I would now also ask my audience, can anyone, what do you think what's happening? It turns out this might be the most complicated operation, but what's happening is nothing. This gives just back the determinant of A. So we can really control what's happening when we perform elementary row operations, what's happening to the determinant in this case. Now, how to see this? So proof, just as notation, let A1R to ANR be the row vectors, be the rows of A. Then, so the determinant of A is just the determinant of these vectors now seen as elements of k to the n. But then, the determinant of, no, this is part A, sorry. The determinant of Sij A, this now means that we just switch the order of the rows here, so we just have the determinant now of, and if we now write the vectors here in there, we have A1R to AI minus 1R, and then AJR, AI plus 1R, to a J minus 1R, AIR, a J plus 1R, to a NR. So to get back the original determinant, we need to flip the order of the vectors. And we've seen what happens with the determinant if we swap two vectors. Namely, this was theorem 9 point, have I written this down? I think it was, 9.3. This is minus the determinant of the row vectors in original order, which is just the determinant, minus the determinant of A. So this is precisely what the derivative is defined to do. So this swaps the sign with respect to the swapping, so this is why we can immediately tell this. Okay, to B. The determinant of mi lambda of A. So multiplying the ith row by lambda, which means as the new row vectors, so as our new inputs of the determinants here as vectors. This is the determinant of A1R to AI minus 1R. Then we have lambda times AIR, and then AI plus 1R to ANR. That's precisely what the multiplication by lambda was meant to be, meant to do. And since this is multilinear in each component, we've seen that if one component, if we multiply with a constant, we can pull this out. So this is that multilinear, so the first property from the wish list. This is just lambda times the determinant, and now we have all the rows back in original order, which is lambda times the determinant of A. Great. Now, why is C so simple? This is basically, if you write this down, it's not that difficult. Namely, the determinant of E, I, J, lambda A. So, this is the determinant, and now what are the row vectors of this one? This is, I think in the definition of these operations, I already wrote this down, what the rows are. This just means the first a minus 1 rows stay as they were. And in the ith row, we now have air plus lambda times ajr. And the rest stays unchanged. But now we can use the multilinearity again. So, namely, this can now be decomposed according to this addition, and we can put out the scalars. Namely, here we can again use, so the determinant is multilinear. So this means this is just first the summand, the determinant of, and the first one stays as it is. So this is just a1r to anr. This just happens when we have removed the other one, plus lambda times the determinant of a1r to a I minus 1r to a j r and a plus 1r and so on to a n r. But, so this here, the first one is just the determinant of a. Okay, what happens here? So if lambda is 0, this is of course gone, then we don't need to talk, but if lambda is non-zero, let's take a look. Here we have the vector aj in this row at this point. Now, okay, this was the assumption, sorry. This is what we need here. I not equal to j, because otherwise this would be the same as part 2. Sorry, this is important. Since I is not equal to j, we have aj in the ith slot, but this means somewhere in the jth slot, which might be somewhere over here or there, so let's assume it's somewhere here. There is another ajr lurking around the corner. So we have twice the same vector, and here we know the determinant is alternating, so if we have two vectors which are the same, 0. So that alternating, the second property from the wish list, plus lambda times 0, and this is just the determinant of A, and so all the traces of the addition of this row is gone. Okay, so this is good news. So this means we can really, trace back what happens when we do elementary row operations. So then we of course want to know what happens with the row echelon form, and so there we can determine the derivative explicit, determine the determinant, compute the determinant explicitly. So in this, we can apply this in a particular case where we can really use this row echelon form. Namely, so far we have seen, so the keyword now, or the word I want to now study in detail is the invertibility of a matrix. We've seen so far, if we know that the matrix is invertible, so we have seen some properties of the inverse matrices, and we've learned how to compute the inverse of a matrix. But this was always the case when we assumed that some matrix is invertible. This is, this is what we have always assumed that this was given. But we haven't seen so far how we can tell, how we can compute if a matrix is invertible or not. This is what we don't know yet. What we've seen is that if we have a quadratic matrix, then the rank must be the number of rows or the number of columns. So if we have an m by n matrix, it's invertible if the rank of the rows is, so the row vector, the rank of the matrix is n. So we can tell this by the rank, but of course the rank requires some really long computations sometimes, but there's an easy way of using a determinant. And as we've seen, the determinant of 2 by 2 and 3 by 3 matrix are easy to compute. So a lot of times this is much easier than bringing a matrix to row echelon form and using this procedure. So, determining the rank to be precise. So let n be a natural number and let A be a quadratic n by n matrix. Now the following statements are equivalent. First of all, A is invertible if and only if the rank of A is n, so the matrix has full rank. This is how one already says, also says this. And this equivalence we've already seen. I've never written this down precisely, but I've used this in the proofs. So this is easy to see. Or not easy to see, but this is what we already know, so to be precise. But the third part is there's an easy criterion by the determinant. Namely, we just need to show that the determinant is non-zero. And this is something that's not hard to compute. Okay, how to see this? So the equivalence of 1 and 2 this is already known. So we just need to show that one of the two implies the third property and that the third property implies one of these two, and this is what we will do. So the first thing we will do is to show that if a matrix is invertible, then it has non-vanishing determinant, and the good news is we basically already did so. Or we can really, it's not hard to do this. Namely, by Theorem definition 861, we can apply elementary row operations to transform A into an upper triangular matrix, since it's invertible, to transform A into an upper triangular matrix, which I call B. So entries are the Bij. And not only is it upper triangular, but we've already seen that was part of the theorem that the entries on the diagonal are non-zero. So we've seen now, since this is upper triangular, the determinant, this was the remark we had before, the determinant of this is just the product of the diagonal entries. And since all of these numbers are non-zero, this is non-zero as well. Now, if we take a look at what happens with elementary row operations. So what happens if we apply row operations to A? So we and transform it into B. What happens along the way? So this might mean we have to multiply with some minus, with a minus sign, and also if this doesn't change. If one of them is non-zero, the other one is non-zero as well. That's what I was going to say. So if we apply this, we have to multiply with -1. If we apply this here, we have to multiply with some field element lambda. If we apply this type of operation, nothing changes. So, but the good news is this is a non-zero number. This was here, yeah, this is a non-zero number. And here, -1 is a non-zero number as well. So by that theorem, by Theorem 9.11, there exists some number which I call mu, which is non-zero, such that the determinant of A must be mu times the determinant of B. Both of them are non-zero, so the result is non-zero. And this is what we wanted to show. So we know what elementary row operations do, and we can see that they do no harm, so to say. Okay, now I have to squeeze a bit. Now I want to show that 3 implies 2. So if the matrix has non-vanishing determinant, then it has full rank. So for this we do the following. We do contraposition. We assume, so contraposition means we assume basically the opposite direction. So we assume a matrix has rank smaller than n and show that the determinant is 0. Assume that the rank of A is smaller than, n. So by Theorem 853, we can bring it into row echelon form. There exists a matrix B in row echelon form I'm using this principle here again. The determinant of A is the determinant as mu times the determinant of B. So again, elementary row operations for some mu in K without 0. But what we also know from this theorem 853 is that the rank of A is the rank of B. But this means we have a matrix in row echelon form where the rank is smaller than n, so smaller than the number of rows, but this only means the last row, or even more the rows, but the last row of this must be completely consisting of zeros. So this means Bnj is equal to 0, or B is, the entry is Bij. So the Bnj must be 0 for all j between 1 and n. But if we take a look at the determinant, I mean, the determinant, yeah, what happens in the determinant? We have in each of these, I haven't done the formula, in this explicit formula, remember that in this product of, we had in each of these summands, in this product of the entries, we had one entry from each row and one from each column. But this means every summand of the determinant there must contain one element from the last row, but they are all 0. But this means, so just from the explicit form of the diagram of the determinant, so let me just squeeze it into here, I'm sorry about that. From the explicit form of the determinant, this means that in each summand there is some 0 among the factors, so each summand is 0. So this only means the determinant is 0. And yeah, this of course means by this the determinant of A is 0. And this shows the claim, because this is now contraposition. So if the rank is smaller than n, then the determinant must be 0. So conversely, this means that if the determinant is non-zero, then the rank must be n. This is what we wanted to show. And this concludes this proof. Sorry for squeezing this a bit. Yeah. Okay, so we've seen now that this is the first useful application, so to say, about the determinant. We can always tell if a matrix is invertible just by using the determinant. Okay, we will now explore some more properties of determinants of matrices, but I first need to erase the blackboard. Before we go on with determinants, I need to fill one little gap, because there's one simple property of matrix multiplication that's one of the most important properties, and that I simply forgot to discuss in chapter 8. This is a very important property, so this next theorem would have fitted into chapter 8, but as I said, I simply forgot to discuss it, so sorry about that for delivering it now. But let's do this anyway. Namely, Theorem 913. So assume we have numbers L, M, N, and N, and we have 4 different matrices. A and B are supposed to be L by M matrices, and C and D are supposed to be M by N matrices. Namely, then the following holds. A plus B, so they are both matrices of the same sizes, so the same number of rows and columns, so I can add them. This is now an L by M matrix multiplied with C, which becomes so, this has the number of rows of C is the same as the number of columns of A and B, so this is fine. This is the same as A times C plus B times C. So there's a kind of, this is what you call distributivity of the matrix multiplication. So yeah, so you can operate with multiplication of matrices in the same way as you do as usual. The rules for multiplication and addition, they hold for matrices as well. That's kind of something which is important and quite elementary, but that was kind of, yeah, so normal for me that I simply forgot about that, so sorry. And the other distributivity in the other components, take A times C plus D. This is also well defined. This is now the sum of 2 M by N matrices, so an M by N matrix, multiplied from the left with an L by M matrix, so the result is an L by N matrix. And this is the same as A times C plus A times D. Okay. Proof. So I will only prove, so let's call these properties 1 and 2. We will only prove 2 since 1 is shown similarly. In fact, it's even a bit easier, but let me do the more complicated one. And yeah, let's do that. So I'm again going, and this is, remember that I defined the matrix product via using maps induced by matrices and compositions of these maps. So let's go via these maps again, and it's kind of an easy way. The alternative way would be really to write them as with the entries Aij, then we have the Bij and the Cij, and then really compute all the components, just do the explicit computation, really just get down to it and compute this. It's totally fine, but let me do the more elegant way, so to say. Okay, so let's consider the induced maps. So A and B induce maps Fa and Fb. They now, so this is an L by M matrix. So these are linear maps from Km to Kl. and Fc and Fd from Kn to Km. Let those be the induced maps, so maps induced by the matrices. So what's easy to see, and this is something I think I haven't done explicitly, but this follows right from the definition. By definition, it holds that the sum or the map induced by a sum of matrices, the map induced by the matrix sum A plus B is the same as the sum of the maps Fa plus Fb. Yeah, and so and of course the same Fc plus D is Fc plus Fd. Okay, I'm just realizing we only need the second one, but anyway, so the sum of the matrices induces the map, which is the sum of the maps that belong to the original matrices. Okay, so if we have that, we now know that the multiplication is the same, so on the map level, this is the same as composition. So we've seen that just by definition of the matrix product of the matrix product, A times C plus D then induces the composition of the maps of the factors. So Fa composed with, and now C plus D, we've just seen this is the sum of the two maps. So we have Fc composed with Fa composed with Fc plus Fd. So if we insert now some vector in here, what is this by definition? We just have to check that basically we get the same map that's induced by this here on the right-hand side. And now let's do the computation. This is by definition just Fa of, and now the sum of the maps, Fc of x, the sum is defined pointwise, plus Fd of x. Now, Fa is a linear map. So here's the sum. We can Fa linear, use linearity to get this into Fa of Fc of x plus Fa of Fd of x. Okay, now let's write this as a composition. So this is Fa composed with Fc of x plus Fa composed with Fd of x. And again, the compositions are induced by the products of the matrices. So as an induced map, I can write this first one as Fa times C, so the map induced by F times C of x. And this is Fa times D of x. And we've just seen here the summation and is compatible with the matrices. So the sum of these two maps is induced by the sum of the matrices. So this is FAC plus AD of x. So, and this was by what we saw in the beginning, induced by A times C plus D. So it follows that A times C plus D must be the same, since if the induced maps coincide, the matrices coincide. This matrix must be the same as this one, and this is precisely what we wanted to show. Okay, and the first claim is shown analogously, but I won't prove it here. So this is really just a standard property of matrix multiplication that we need in the following, and I simply forgot in chapter 8. So, sorry about that. Now, back to determinants. So, this is now, the next one is one of the most important property of determinants, I would say. Theorem 914. So, for all A and B, which are n by n matrices, so quadratic matrices again, n is just some number in n. And for all these matrices, the following holds: the determinant of the product A times B. So the determinant of a product matrix is simply the product of the determinants. So it's as simple as it gets. Okay, and this is great news, because One of the things it implies, if we can kind of, now if we can use this product rule for the sum and for products of two matrices, we can do this if we have product of 3, 4, 5 and many matrices, just by using this over and over again. So if you would have the determinant of A1 times A2 times A3 and so on to AN, we would get that the result would be the product of all the determinants. Which means if we can write somehow our matrix as a product of much simpler matrices, which are, I don't know, which have some properties, like for example, to compute determinants, it's always good to have matrices in which there are many zeros. So very roughly, because then many summands in this big fancy sum vanish. So if you can maybe decompose this as a product of matrices with many zero entries or something, and like as a product of matrices whose determinant we can just immediately see. Then we can get the determinant of the full matrix of the product here as well. So that's kind of strategy of how to compute determinants by just breaking it up into factors and computing the determinants of the factors. Now, how do we see this? So, of course, you could also now do the same, but this is a really messy proof then. If you take the entries A to be Aij and the Bij and would then really write down the formula in terms of the, this matrix here, you can compute the different entries, and with these entries, you could then write down the explicit formula of the determinant with permutations and so on. But this formula would then be a nightmare. This would be really complicated. Same way here, we would have some really big sums multiplied with each other, and it's really ugly, but you could do this. This would work. So you could really work this out by really breaking down, so really brute force, how you would call it, so really computing every entry individually and seeing that it works. We're using the more elegant way. Namely, we can do the following. So, first of all, that we consider B as a fixed matrix. So, if B, in the first case, if B is not invertible, then we've seen earlier in this section that then the determinant is 0. So in this case, the right-hand side would be 0. But then the left-hand side would also be 0. Namely, if B is not invertible, then the rank must be smaller than n. So that's the dimension of the image of the induced map, if you recall. So, but then it is easy to see that if we then compose with another map, we cannot get a bigger rank. So that's easy to see that rank of the product A times B is also smaller than n. Whoops. For all matrices A. Right, so this is something where you can, if you study the definition of the rank or think about it, then this is really not very hard to see. So then the equation we want to show becomes, 0 is equal to 0, which is obviously true. So this case is clear. Now, for the more interesting case. So assume B is invertible. So, as we've seen, Nimbus theorem, 912. So that the determinant of B is not equal to 0 by theorem 912. Okay, and now we define a map. I will call DB, which takes another matrix n by n matrix and maps to K. And DB should be defined as follows. DB of A is equal to the determinant of A times B divided by the determinant of B. Since this is non-zero, it's well defined. So yeah, this is just a map. Now, if we want to show the equation where if we want to show this here, so this expression, this map dB, would just be by dividing by that B, which we can do if it's non-zero. So we would need to show that this expression just coincides with that of A. So we need to show dB is equal to that the determinant we had before. So, and the idea of what we will do this, the idea of what we will do so is how we do. It's just that we show that this has all the three defining properties of a determinant. We've then later on shown that there's only one function, so if we can show that dB has these properties as well, it must already be the determinant. So we will do this by showing dB has properties 1, 2, 3 from the wish list, so from definition 9.2. Okay, this is what we need to show. Now, let's go through these properties. So first of all, an observation. If a matrix A has row vectors, we might call them A1 to AN without the R all the time, but these are, if these are the rows of the matrix, then, and this is not something I would ask the audience if I would have one, A times B, which is again a quadratic matrix, what are the row vectors of these? And if you think about the definition of matrix multiplication, so if we now view really these row vectors as 1 by n matrices, so really as matrices, then as matrix multiplication, it turns out just if you take a look at how the matrix product is defined, these rows are simply A1 times B, A2 times B, and so on. AN times B. So we multiply a 1 by n matrix with an n by n matrix, and the result is again a 1 by n matrix, so a row vector. And it really turns out, if you really write this down in detail, so if you don't see why, maybe pause at this point and just write down the definition of matrix multiplication for these cases, and then you will see that this is precisely how the matrix product is defined. So we know now, that the row vectors are of this form, and so we can now prove the properties of the determinant. And now, of course, these properties were formulated for inserting vectors, so we will now do this by inserting the corresponding row vectors of the matrix. So we need to discuss what happens if we put in these rows. Now, I'm sorry, I had already finished recording the proof and started erasing the blackboard when I realized I had made a complete mistake in my computation. So I'm recording this again. Sorry about that. So this was the row vectors, and now in the following computation I want to take some fixed element A and not write this every single time, and let this denote the rows. So we need to show the three properties, starting with this multilinearity property. Now, I'm now writing this in terms of rows, namely in the following way, that I be some row, so I is between 1 and n, lambda and mu should be in K, and bi should be a row vector. And now, being a bit sloppy with the difference between row vectors and elements of K to the n, but the idea is now what happens if I have a linear combination now in the ith row of the matrix. And now I'm switching a bit between determinants of matrices and vectors, but this is hopefully clear if you understood the definition. So if we have this, then we need to show that this dB is multilinear. So by definition, dB of A1 to AI minus 1, and on the ith component we take lambda AI plus mu times BI, then AI plus 1 and so on to AN. So now we need to show that we can do the same computational trick and kind of pull out the lambda and the mu and so on and replace with the sum in the same way as the determinant. Now, what is this by definition? By definition, this is 1 over det B, which is some constant factor. B is just a chosen fixed matrix. And here we get then det of, and now the matrix with these rows multiplied with B. But we've seen if we have some matrix with the rows before, the new rows after multiplication with B are just obtained by multiplying each row individually. So this means that the determinant of the product of this with B is just A1 times B and so on to AI minus 1 times B, AI times, and now's the interesting part, sorry, not AI, lambda AI plus mu BI times the matrix B and so on to a n times B. Now, this is now where I need this previous theorem. Namely, this is a matrix multiplication, and my previous result here, that was part 1 of theorem 13, tells me, so this is theorem 9.13. This tells me that the one in the ith component, this is the same as 1 over det b times the determinant of a1 times b, and so on until we get lambda ai times b plus mu bi times b. And the rest goes on to an times b. Okay, now we can use the multilinearity of the determinant. This looks odd, but this is just a sum of 2 row vectors multiplied with constants. And so we can apply the multilinearity of the determinant now for this part, because this is really the determinant. So here, since determinant is multilinear, this is the same as lambda over det b, det a1 times b, and so on to ai times b, and so on to an times b, plus mu over det b, det a1 times b, and now in the ith component we have bi times b, an times b. So if we now take a look at the definition here, this is now the same as dB of the matrix which has these as entries. Namely, this is the same, let me squeeze this final part right in here. This is dB of a1 to an, so the matrix with these rows. And this is the same as mu times dB of a1, where bi is in the ith component instead of ai. And this is what we wanted to show. So this is the same as, here's the lambda missing, lambda times. This is the same as this, and this is precisely the multilinearity property, so property 1. So this has been shown. Let me erase and then show you properties 2 and 3.